Okay, thank you again for having me here during the second part of this last week. That week we discussed a little bit about this geometric string theory initiated by Juan, and was the first approximation to try to compute some product homology for rigid spaces, at least with some touch data for the flavor. Using tools coming from actual differential equations, actual local representations, actual real algebra. So in today's talk, we're going to discuss about the first application that what we were developing things, was studying the homology of modular curves, but then what was kind of extended analysis. So maybe to start with some maybe very broad motivation. And I think that the motivation, at least for this talk, is basically that we want to understand direct model. Very good morning. Of course, this is a very big statement, but maybe let me first tell you what are the different sources of these things, because depending who you are and where you are, this work can actually have different meanings. So there are some main sources that I know. Oops. From different commodities attached to more varieties, flavors, and just to mention a couple of them. So maybe a first kind of construction of the automorphic forms comes back to maybe associations like quasi-coherent. Those are quasi-coherent homologies. So here we have the classical modular form. Forms. Basically coming from certain ectomorphic vector bundles of more varieties. Homology, for example, the usual modular forms of weight k and integer and 0 is this kind of guys. But then you have, well, you want to study these guys, particularly you want to study congress of these guys. So you know, it's natural just to try to make any counts. So one way to make these forms boundaries goes back to here, with the so-called chaotic modular forms, or like ordinary forms. Which essentially is just basically global sections of line bundles in the ordinary locus of the modular curve. That may be the case of kind of project or something like this. Essentially, again, fits into the framework of coherent homology, some version of the modular curve of the smart variety. And then we have these very modular forms. And was basically following somehow this idea to make it over conversion. Maybe it's not precise, but still something that is concentrating around the ordinary locus modular curve, but not just radically like mod B, but actually over converted to the region. So this is some kind of like the fast coherent realization. We also have like a native realization. For which we have the Sarsen comparison theorem to prove that essentially the two have to carry the same information at the level of these modular forms. And here we have things like modular symbols, there's kind of distribution floating around in the time community of these guys, but also the one that would be more important for us, which is the discoverability problem. This one is the one I will talk about most of. Diagram wrote, and well, maybe just mention it loud to write it. There are way to make families of periodic autonomic problems, but instead of taking like coherent cohomology or cyclic cohomology, consider something like the rank cohomology, and you try to interpolate the connections. So these are things that maybe the literature I know that's nearly overconvergent, that modern problems. And for example, at the idea we have different papers working on. So we have all these different sources of periodic autonomic problems, and well, maybe if our goal is to understand these different incarnations, or just to understand what actually these guys are, I think that first it's important just to put them in order. What is order? What that means that, well, all these come from different topology theories attached to more varieties, in particular attached to just real spaces. And there are different ways to compare these guys. For example, you have these Shimura relations or this BGG relation with packings relating the time cohomology of higher level with the classical other classical coherent cohomology. So there are actually tools from Hodge theory, periodic Hodge theory that relate to all these guys. So we want to put them in order, and I think that nowadays the way, at least a way to put all these things in order is using precisely this session. All this theory. So maybe let me not go too far of this because I will find that tomorrow. But a first shadow of this organization of all these theories appearing in this gadget is precisely this geometric section, which corresponds to this Hodge text. So today I'm going to maybe say more words about that instead of this. At the end, potentially I will give a comment about that. But even before, I think it's worth to first introduce the main object of study. What about computing knowledge? Now I'm going to introduce the visual notation, what we do in about making more varieties, both cases, about that. So let's see the reductive group over here. And take GeoX, some more data. Or maybe if I had an example in mind, but what example that we consider work was the case of model curve that the group is going to be GeoQ, and stays a pair of characters, basically going to be the upper and lower half of the going to be concrete. The Shimura varieties you get for this general, the ones you get for here are those moduli, basically moduli of the liquid. And also push GSP to G if you want, and then single half spaces to get any CKL varieties parameterizing abelian varieties polarization. That would be something to remind. So again, produce notation. So E your X is the reference field. essentially it will reveal the field definition of the canonical model of digital varieties. And for K of open, need open subgroup, compact open subgroup of the delts, we let moral K over E is canonical model. Example in case of modular curves, here you can take the congruences group because my case is producing one modulus number, and here you end up just with the moduli of elliptic curves with a trivialization of the tape module of that order, the torsion points of that elliptic curve. I'm not going to use this field at all. I'm going to focus on the guided defense. So there was things like of L being over to B, and some embedding of E, let's put this right, of L. And we are going to let just Mura of K being over L be the base change. This one to these aligned coefficients, and then I take this just incarnation as a register. And again, important to see guys. Okay, so basically, we just took the analytic incarnation of this more. Okay, that's useful for the avoid increasing more notation in this talk are the following two assumptions. One of them is let me first assume that the Shimura variety is compact. So this is going to be false in the case of the modular curve. If they are not compact, in general case, you just use Taylor multiplication to study objects. For modular curve, the canonical multiplication, but just having the scope, the minimal or toroidal is the natural one we're going to use. This way, I just avoid this. Sorry? This means it's going to be a minimal complexity. But this just means that we're right. So this is just to avoid finding more things. And the second one, again, is something again technical, important, but basically, let me just assume the following for this happens. So you will supernodes of the system of G. And well, these are different consequences, but the important ones that we want to keep for us, that we can forget about what actually this means. What matters is that if you have some open form of the group, then this map is actually going to be a K model of K prime. It's actually going to be a group that's basically because I don't want to get deal with more equation. Okay. Again, we're in the guiding sequence, so people are going to fix that. Never can be. Prime B. For KP, a group of TQP. Yes. Yeah. Just this guy is more variety of them. Then we're going to be something outside, just focusing what happens in the vary the level. Okay. So this is all about orientation. Maybe define. Is that well, the fixed level outside this, so for us, what is important? What is important is this. Any compact open subgroup, yeah, maybe split it out. You have an algebraic object that actually the regional inclination structure analytic objects living over this Gaussian field. So you end up with a whole tower. More varieties. With this Gaussian field node. So this is actually at least the first chunk of important information you get from all these it's so we have the tower. We would like to make the tower more independent of all these open groups. So it shows a working paper. Define objects that ought to be the limit of these guys. All these finite levels should not varieties. In a spherical sense, maybe the case that we did it was in the case of quantitative more varieties. And in that case, it proved that well, this limit in a spherical sense provides for you a perfect space. So in current language, the way to state that is you have these rigid spaces. All from rigid spaces, you can again map of perfectoids. Just consider what is going to be the diamond. So that's then you can take the limit of all these objects together.
So this definition does depend on K operator, right?
Yes, but I want to ignore this
notation.
Yes. So very I should put the KP here.
Okay.
But since this is going to be fixed, I just want to make it 30. But yes. So yeah, essentially this is going to be an object, a diamond. Shift this shift on perfect spaces E. That this string is such type. More general, we have a type by it's Hanson. Then this guy is actually pressure respect all these vectors, diamonds. But so far we just know it is pre-abelian type. And the reason of this basically because we know for single variety, what also the paper, all from single variety, you can just try to spread out as much as you can. Probability is the best. You know, what I essentially means that in best close to space in a single variety, roughly speaking, this one's kind of connected components better.
If you vary the limits KP, are the corresponding maps finite at all?
If you vary the KPs,
yes, so the system, the maps are like finite.
Yeah, also it's not going to be finite. For these guys, for the compactifications, it's more so. I mean, they are complicated, but it's so that everything's finite data.
You expect that it always perfect?
Yes, yes. Even that, I mean, even this is not actually, let's say that, like important to get more variety. So I think the only example we know it's actually just going from the guy who's doing this guys. I'm going to mention this.
It's like perfect in the sense like it has some parental cover, right? You attach to some. It's like the same, but this Shimura thing is perfect place. It's just like.
I mean, this means that this size is defines shifting here and means that it represents a perfect space. Maybe it's slightly different from what we think that means that they call it the completion of the collective function. Yes. This is stronger. This is much stronger. Yes.
Oh.
I mean, I don't know as much, but this.
And is it true also
in the Hodgkin, yes. Okay. The Hodgkin cases, and here I'm not sure, maybe yes.
Do we have counter examples of the Shimura case?
I think I imagine that we also expect this to be true in general,
okay.
But at least this is. Okay. So the problem is to talk about the field homology. So let me define it using settings. What a definition. This definition is words complete homology. Of course, it was specified the data, the level. Is just the prototype homology design. The homology. Prototype homology is hello guys, of course, for efficiency speed, so the metric was homology. Here, well, depending on the kind of coefficient you're looking at, you might put set P, set P, P. Then you maybe just put P, P, and also copy this, make different versions. So this is complete homology. The homology is the guys. Maybe we can be more concrete why this is related with the definition of that. So the definition is maybe for that, let me just remark. Learning from this definition, well, we have a whole action of GQP, goes for construction as a limit of what is called this variety, but also we have at least an action of the Galois group QP, which construction is very of in general, actually what we have has something more. Second, these guys, let me just focus, are here. Have an action of GQP, but also have an action of the reference. It's not just an action of the L, the added place that we choose, but actually the whole group here. Maybe not obvious from this presentation, but um, so, well, the real definition, maybe the video symbol set B. One. So this by homology. Let me say the theorem goes back to Camargo and his groups, is that these homologies are admissible ones actually can be computed as well. Another way to try to make families of this is to take the final level of more varieties. Take that homology modulo yes. And you can try to go that infinite level like this here. And then you can more or less radically complete by taking the difference. Turns out that this computation, same as this one, maybe this won't be, should not be that hard, but this limit is actually important. But something important on the structure of these guys, and this follows from the fact that it is an admissible representation. This admissibility is some kind of analysis condition depending on the representations, more precisely. Take the modulo T, take variance by an objective group based on the time rational. And this admissibility actually implies that these limits that may appear when you try to write down these parameter guys, the higher limits that you can actually write this in different sense, and maybe from this presentation, this one is also isolated. So maybe to the type homology. It's more variety, a bright guy. This presentation is more clear than yours. Okay, so again, we're starting with the principle that the entire homology of more varieties, because for example of this more relation of these constrained compositions that we get from the entire homology of varieties, we have spaces that relates this homology with automorphic vector bundles of forms. That these homology groups should actually interpolate radically, should encode families of static families of automorphic. So this is the principle of so it want to start with this.
Can you say a little bit more about why that, why the constructor completed homology interplays between?
Yes.
Yeah.
So let me say this with an example of a curve. Then take something like this, just the modular curve, and again. And then take this the end is computation. And something that, well, about design, have this infinite level modular group that's going to be gamma and this one kernel of so all this power curve for any representation of your2 can attach to a consistent. So right. For example, we can zero something like the symmetric power of the standard representation, and we take its beta algebraization. Okay. So this guy is seen as a chief. Well, yeah. There are some legalities about the cost. Let me just pretend that it's a product outside. For why is actually the product outside? Outside. Then, so these homology groups are indeed interpolating kind of like construction the entire homology of all these views. So at least this one produce an algebraic interpolation of all these homologies because, well, for example, any symmetric representation with the lattice, mod P is going to be trivial whenever you take a subgroup that is big enough, small enough. So all these guys actually, all the at least mod P modular forms not appear in this kind of guys. What is slightly less clear is why it is related with the classical modular forms. This one is more clear. Which is essentially the Hodge-Taylor decompositions of things. This says that maybe the important one is the first prototype homology. Is more varieties. Now, the city can write it down some things. Now, take the person is just H naught big by cost. It's a much twist in that information. Maybe one. It's one or I forgot the twist. So I may just know the twist. Yeah. There are some costs. There are some costs over the problem. So one is that this guy, because the Hodge-Taylor decomposition, you can just write it down as basically homology of the vector maps. So indeed, these homologies are going to produce at least going to be related with the model here.
Make sure you're homology of Y, not X.
Yes, I mean, yes, of Y. It's important of Y.
It's the open part, not the compact.
Yes. Yes. If you want to make the compact appear, then instead of taking prototype homology, you will take this pro-Kummer-type homology. But the pro-Kummer-type homology is the same as the product. So basically, this is what I mentioned that you have the cost, you need to do it with some other complications to deal with these things. You need to deal with those functions. So the homology of the modification is the same as this one. That's one. Okay. So let's go back to motivation. So we want to study these groups. And maybe instead of course, personally, the Dorchkan of these groups is important, but at least for writing with classical automorphic forms with complex numbers, maybe what is more important is to study they don't also work. These those modular forms that actually have a realization that is zero.
There is no state twist.
There is state twist, but if we're going to set the way this. Yes, but yes, there is a state twist. I don't want to say. I forgot. Maybe it was a 1, and it was maybe it was 1. But yes, it is a twist. And also maybe the device was good. Want to study this side. And then a fruitful way to study representation, which basically is just a line representation, maybe complex, is by studying these local identity vectors. Again, this idea that goes back to last hour, that means by side vector, the theory of local identity representations, and then re-taken by Emerson, basic concept of program compatibility, and then actually studying the local analytic vectors of this kind of things, maybe a theory of this kind of Banach spaces, can give you at least access to use the tools from the algebras or actual differential operators to attack understand this. So the idea of Kant was twofold. So first, of course, for this, you will study analytic vectors with homology, but not just that, but actually related. With honest gravity theory is formed. And more precisely, not the gravity theory, but with this model of theory. Okay. So, well, so let's say that yep.
Like without this geometric set theory, without this geometric set theory, you do the same story for modular simples.
Yes.
Then like in general you beta balance.
Yes,
So
yeah, the relative beta have studied these kind of questions, and in particular, I constructed this so-called auto-convergent relation graphs, which are kind of.
But they did much.
Yes.
They have a finite slope assumption. No, that's not a fluent square, it's a finite slope assumption.
Yes. So even in those work, but simply they're studying again a bad interpretation of this, and still what they're doing is kind of version of this whole thing. So these modular symbols are composed of some kind of distributions, but this distribution is just two of local representation. So they're doing some kind of dual version of this. At the end, it's also encapsulating.
Even without complete geometric operator.
Yes, yes. So maybe again, motivated from these Hodge state decompositions, the first thing that would be accessible to study was just the Hodge state behavior, the Hodge state structure of computed topology. Meaning, you made this first just tensor CP instead of other fancy pyramids. Like, please use these kind of things. So, take this product topology for the CP. Tensor with CP. And of course, this tensor has to be a nice tensor product, but it's a complete tensor product. That's it. We know what we're doing. So, so by short the this comparison theorem. That well, here, again, they're just compact number varieties. It's fine. Then I'll give you the correct classification again. Maybe appeal to the work of Yao Yao, which deals with destroying complication of this. So this also can be computed as with the product homology of a nice shifter that I think we often call just OHAT. So this OHAT is a kind of completed shift over giving over this diamond that basically just takes a perfect weight exactly zero as it is underlying weight. So just the completed shift this guy. So again, well, this is kind of the first way to translate homology into try to make the geometry here, try to start the shift. But then we want to take a local kinetic vector. So a very what Lua does is taking some kind of the right version of local kinetic and study, let's say, vanishing of this right version in these cases. But it turns out that this theory of this local representation theory can be again promote for a very nice algebraic theory, right? What we have logical algebra using the formalism dense mathematics. Using only analytic calculations. Work with the okay, Rodriguez. So Rodriguez. You can actually put the symbol this guy meaning that you can actually take local kinetic vector of these guys in an honest, somehow topological, maybe condensed way. And concretely, it is actually what you would expect to take and do considering his work. You just tensor this representation with the local analytic functions of the group X. So
Left-hand side is curiosity.
yeah, right. But you can tensor with these local analytic functions. Could be that again, maybe because these ones are very nice and kind of banal complex things, you do not need that much to make sense of this in context. But right, just like a nice context. And so this guy have an action of the whole group. So this one is acting here naturally, but also it's going to act here at the left reference. So the idea is basically we're just going to take all the vectors in here whose orbit is locally analytic, right? It's not definition, but actually it turns out to following the definition actually turns out to be a good definition. So you can define this locally analytic stuff, and you may wonder, whether this is going to give you something strange because you take a random homology in this Banach space. But those are the defaults of this theorem of Hamilton about divisibility. Like these local analytic vectors, things, modules of these guys. This just the usual completed homology for these cases. P, C. And just take local analytic vectors of these spaces as functions. So again, even though you try to do something fancy, you end up not being that fancy because you just take it. What is good is that now that this has some kind of right improvement of that, it's useful to do some argument. So the theorem, maybe for the theorem, we want to relate this to the geometry Shimura varieties instead of the Banach version. So basically, we would like to, let's say, intuitively just put the LA inside. Actually, you can't. That's good thing about writing something that you can somehow just how to mix things and something actually correct. So then we consider all A. But maybe secretly thinking about basis shifts over the topological space. Right, partially make the definition correct. The association B all actually things like that. Diretta more late, but maybe the first approximation is just a locality ring space. Have the same topological space as this one, and maybe these functions. But again, you can promote this to an actual and honest analytic space. Sausage process. Here in the plugin, actually you can just switch the rate. One is smaller first. So that is local analytic computed homology is the same as just the chip homology. So let me just call it analytic homology. Same that you just do as chip homology. Is say topological space and this shape of functions. Then you can call a
It also, that also correct the analytic stack.
yes. It means it's just the coordinate homology of this analytic stack. So here's a corollary. This computation was basically by an argument that Rebecca Schultz gave in distortion paper. You get that, or at least the vanishing part of the Hungarian method. So I figured that the dimension of this variety these homologies, right? Product homology. This guy is, well, that these can access here using the rational version for the integral version of the actual detections. So, again, we supports this. So basically, first need to know if it is admissible. So like this one's then B is 0, you can only if it doesn't have localized vectors. Tells you that these all the interesting vectors in the actual group G are I did that version. This concrete. So to prove this, you can prove the localized version of that. Then of course, well, you can just cancel the CP. So it ends up that this one is just the same as the homology of this very phase. So the second thing you need to know is that basically this space has a topological space, which is nothing but the limit, the topological space of these more varieties that this guy has dimension. By dimension, maybe I mean topological dimension. Together, 0, at least, then this one just won't vanish beyond the degree of.
So That's as a logical space or as a
Topological space.
logical space. What is the?
Homological dimension.
You cannot make this argument on the outside.
No. This is important topological space. The product side you make here. You don't have, I mean, you may have some order dimension coming from kind of the symmetry of the product side. Group homology of different. Here you actually need to work with honest topological spaces to make this set.
And also just to make sure that the more argument the thermal, the always answer is the T.
Yes. It does
Either either or all or
yes, it does. Yeah, that's geometric.
although you put in a pure.
Yes, looking to the previous one. Sorry.
It doesn't make sense.
Yeah. Okay.
Can you say when you say yes in this make this sorry so this variability so it's really taking the underlying logical space and then
I'm saying that this one is a first approximation to think about the space. Just take the same space, just take its sheet of function. And in this context, this formula makes sense. Basically, it goes the you want to
can you say a word about can you say a word about the concept of this how should I think about it?
in the sense that this guy actually is going to produce for you some analytic type. And this is nothing but the coherent homology of this guy. So the thing that this one is basically computed by the coherent homology of this object. Instead of some sheet in the random space. It's an actual coherent homology of actual homology. So let me put this to one. So this the application of these things. So of course, the content of the theorem is not just the vanishing of these things, but actually to study these things using differential operators, you can actually try to study this shit with these differential operators.
Can I ask a related question still with this concept of this theorem? So when you consider the Hofstad's map, like you can think of OLA also as a
Yeah, you can put
topology upstairs, and when you push that upstairs, so this would say that this is also computed by technology of P, like in the case of gel, P1 with best logical space with
when you put forward the thing, yes.
and there how should I give this OLA on that logical space?
It's again just I mean you can't just it's coherent sheet of it, even if it's going to be like equal, then you go to that
Got it.
this is going to be a much coherent.
Okay, sorry. Is there any? Can you say a little bit more about this, the analytic stack as the LA, and so the idea that this is some sort of like you had the diamonds before, and this is sort of the perfection of the diamond.
Yes. So this guy is going to be encoding something that hopefully we'll get to mention at the end. Is well, at least the Hodge state incarnation of some. And this is going to be some torture of the Hodge state. Take some KP, the group, offline because of the Hodge state. So this is what. But let me try to go to that. Sorry. So the tool for proof this. Of course, beyond actually the framework of vector spaces and all the things. This is the new tool that's doing this. It's geometric. This thing, geometrics and theory is not going to do those proof the theorem for you. It's actually going to give this something with a model structure. As you can say, it's going to be actually related, which cannot be models of that, right?
Something, so here, you use some properties of the assumption that is.
For doing that, I do not use anything, except that it has more right.
So if it's not proper, and then you can still get this convolution problem.
Yes, except that here you get kind of toroidal complications. Maybe here toroidal complication.
You cannot just get an open part.
No. You need to quantify this cost of this. You need to take. I mean, these structures in general will involve toroidal complication, maybe input both sides, and we'll use this for continual language about local expressions.
And for the open part, you cannot say something about like Cooper or talk about it.
I mean, at the end, like the tower of the Schmor varieties for the open part is kind of equivalent to the tower of the Schmor varieties of the product computation. It is a kind of that allows you to basically, one and one piece product multiplication, the whole tower.
So you still get the same bound.
Yeah, you still get the same amount, yes, because in the game is a limit of which spaces of dimension Schmor varieties. Okay, so maybe going to just mention what before about geometric theory or that time. So we start with the Ricci space over C, not the right critical field, the Ricci space. It would be some vector bundle the product outside. Maybe this guy would be general the product. Then this guy, we can plot something about the addition operator. B that goes from this guy to this one, but is his field. What is important is that it computes co-product convergence process. Compute product measures. So basically, compute product homology, you can first compute the homology of this field and then just push forward the dynamics. Good. And of this, you could maybe obtain a version for whenever you have a torso involving the end of the torso. That's the second. With an observation that
These things are these are asked. So there's some relation between what you just raised on actually with local analysis part.
Sorry?
Like is there some relation between local analysis complexity and actual?
there's going to be a relation when there's yes, there. Let's say that the relation will come from the geometry of the right? But there is where everything is going to happen. Somehow the English moral is a consequence of different ways to say this, but one of them is because the way D models are going to localize the right? So hopefully fashion. And this is because of one way to do it is to do this. I mean, already is kind of consequence of maybe primitive or something like that, the bracket. Can also be understood in this machine of set theory of state theory.
Here you go down something about the decomposition of homology. So
Yes.
so I think about that also the decomposition of local analysis homology.
I mean, it's not the whole thing may not decompose in the same way that you have a random very big people with the variety not have like small pieces of corresponding kind of bundles or even atomic models of this. But once you start putting out chunks of this, you start getting something smaller. This one may have some kind of position in the variety. This is what this thing sort of started. So if not, you get something very big. Then try to put up pieces and when you try to put up pieces, this sort of hellish moral relations are going to start appearing. So, observation of one. Is that actually this geometric extension operator should be promoted to something else that also encodes the arithmetic extension operator. equal for L. Yeah, was P. Or even you can take this writing. Then for P as before, so let's be first P. It's matrix extension. For this extension, because it says that for the site, not coming from not coming from the outside. All people branches is for one. And for this guy is landing in a twist of the quotient. And again, this should encode kind of the geometry. So actually, you should expect that maybe despite more local computations than this part should encode somehow the arithmetic set. This guy. Celebrate. Going from B. And now taking positives maybe not in mega one, but some twist. So yeah, maybe I'm not going to take something about the construction is going to be similar to the one that so last time. Basically, you start with historic coordinates. By looking at historic coordinates, you can just compute by taking local vectors. The algebra of this will help with theory. That's how we calculate that. And then you just use the fact that in historic coordinates, you can explicitly compute the factor state using these p roots of the dots. You end up with this problem. Maybe something important to say that if you take this composition, this is the geometric operator. Right? This has a quotient, remember the expression, this is one. Maybe for line bundles, something like O of P. So here you're going to act by opposite I and not by I. Or I that is actually included into F E minus one that's above the right? Or A twist that this acts as A twist. Multiplication by I, the plant inside sensor. And something funny that, well, you take two copies of the quantum station, we'll end up with this quotient like that. This quotient, well, this is an extension of this guy, so it has at least the push out. Sitting inside this. So this push out as a quotient of this of omega 1 minus 1 and W4, but here they can take the anti-diagonal. So by taking the anti-diagonal, what I'm doing is just taking the extension here and subtracting one extension with the other. So I get the zero extension. I'm going to get something that actually is trivial. So this absolute thing of this the balance extension that map something like this. Again, here I have this copy of omega 1 that is for anticipation. Here it's going to appear by the natural projection. Maybe it's going to be final natural projection. And such that essentially, if you project again in this right direction, which is the one that is going to give you the projection operator path extension, but if you project into this positive direction, you basically are going to get just the state, the same operator of this quotient here. This one is going to give you the same operator. This one is going to give you the geometric center. Something kind of concrete. Okay, do this using coordinates. Just forward.
Wait, what is the conclusion then from what we got?
It's coming goes up this.
They use that on the conclusion.
Yes.
But does not map depending on I.
Sorry?
The map depends on I.
What is I? Here?
Yes.
I mean, this is the conclusion, but I, this one, I sits here. Because O sits there. Right, so 3 minus 1 to get an O. So, let's visualize this theory. The case of more varieties. So, it has a corollary. So consider this but maybe I want to actually emphasize that help like this. Then there is a full operator. Or operator. It's a field or something related to that. That is just going to depend on this torso. That is going to map, well, it's a heavy torso. I can take the adjoint representation here and look at this underlying proton shift side. Here. And this has the feature that for all local analytic representation, one has, then I stated that just for a vector bundle, but for these kind of things. We have B, we have this full sign operator. That, and then we can just take the derivation of B with the D B again, and then just compose the full sign. In other words, so if we dualize this picture, telling you that the dual of this guy is not equal to just elements in the real about G, and that the action of this in this model is given by open linear definition.
Is the domain beautiful that G.
Sorry, this
The line above.
this is dual. Thank you. Okay. This naturality of these constructions can have this project. So now, sorry, how much time do I have left? Just to be sure. Then, so again, well, maybe this is like for computing what we need for the theorem, we just need the geometric operators. But this is going to tell you that once you take homology of some shift path, actually this homology is going to have a residual arithmetic action, and that this arithmetic action is coming from this, right? To particularly shift OLA, thanks for go back. Fine. So we want to compute these technology T of what or A. So maybe the first thing you can do is using again briefly comparison theorem.
So somehow in this corollary, the attic, we look at attic part doesn't appear.
Sorry, it's probably what?
In this corollary, like shouldn't our
Okay. No. This is a corollary about vector bundles
it's
in the product side, or maybe shifting the product side. Yeah, no,
yes,
don't talk to
yes,
me.
yes, yes.
So this is by the primitive comparison, you can actually compute it. Maybe close like push 0 junction. But technically, root homology with KP, tensor with some representation of KP, we can just by using unified junctions. Right now, the reverse homology of the thing at high level. See if we don't have any functions, KP, but it's then make it a quasi. Basically, the local functions are going to be inside. Primitive comparison, this one is just a full unit of our spaces, so it goes here because this space is going to compact.
It's a plug in.
And it's not calling over K. It doesn't matter because if you take calling over K, this doesn't change. And yeah, then use the amount of the list, which is that make this guy is a KP dorsal, so you compute homology here by computing first here and then take KP homology. This one is just a KP homology. So we call this maybe V. It's medium with this V because of the P, but okay. So I want to compute this. First, take the projection from the vertical side. That side is already. So okay. This is just the same as the side. The homology of the smaller variety VKP of this to forward of the shift piece. But what we know is that this to forward, at least the homologies of this to forward can be computed by the first taking the homology of the separator, then apply V. So what we need to compute these homologies for this thing is basically compute the separator. More.
So there you're like essentially comparing liquid homology. There you're essentially comparing liquid homology with the
Just essentially what's happening. Maybe even the whole theta. So yeah, we don't have time to say proof in this, but let me say at least what gives.
You have at least 10 minutes.
Sure.
You have at least 10 minutes.
Okay. So for this we need the famous field state of your map. Number ID. Right. B. Well, maybe in the case of the modular curve. One. And well, this one's come from the approach to composition. Fix new approach from vector. We get P, either P1. So this one basically is harmonic. Of preserving these integrations. We have n is mathematical. N to be the living quotient as a section given by the centralized element. Okay. So these things, in the type variety, everything like that. Written like this. Something to remark about variety that, well, we want to compute this set operator. So for this, we just need to know compute it for some kind of faithful representation of the E algebra. So we can in particular compute it for all the algebraic representation, for all finite algebraic representation. And because, well, the way this remarks construct, basically all the algebraic representations come from, so this one is right? What to say? All these algebraic representation here comes from some equivariant vector bundles from here. So it suffices just to compute the same operator for the pullbacks of these G equivariant vector bundles. So, okay. So we can just remark what you get. So the first case, maybe first let me know that the vector variety divided by G basically the same as this except this. So G equivariant vector bundles, same as quasi coherence, is the vector variety G is the same as just the quasi coherence of the start the same representations. Right. And remarks, the first for M coming from the number, coming from a representation in the left. I shall say when for you in general case, basically compute this associated vector boundary vector variety, and what you get is, well, you also for the Shimura variety have another limit also coming from the Hodge composition of the Markov model. This one is going to be the rough realization. When the actual, I don't know, maybe put the multi. This one. So for example, if we are in this P1 and we start with some line bundle like O K, we end up with a shift of K on the props. So it will be basically the order of K is going to be omega K. In this case, here you just get a natural function of this. So this one comes twisted by, well, this one you convert in reducibles, and particular example, the weight comes twisted by the weight attached to the element out here. This. So for these guys, we know how to compute these ones. So what is left is to compute the pullback. Well, and for these ones, we know how the set operator looks, because here everything comes from something living over L, living over the reference field. So the value action here is completely trivial for geometrical and elemental. And we just have this action coming from the arithmetic operator by just the minus mu. So to complete and to actually compute this operator, we need to understand extensions. So second, we need extensions. Identify this. Take something like this, continue the right functions of n, where well, you have a one action of n, where n is acting in n, when you see inside here, so it's that n just a dot, and just the have an action of n one action that is mixed between just a regular action and the adjoint action. And it turns out that if you take the pullback of this thing, the end of the vector bundle, the flat variety attached to the representation of P, using this equivalence here. You end up with nothing but the greatest zero of all P around it. So you can also see a very complex shape to end up. So as a corollary, and because we already know what the full set operators are for all these things, because C is kind of constructed for the Balvin's extension. This one is not like spread the algebra, twist Balvin's extension, with mod out with class of 1, given by the symmetric algebra, the element 1, right? And so, yes, that's so. The code that we have the Lie algebra of n, if it's a P, if it's a G. P.
For this theorem, you should do some computation.
Yes. You need to do some computations using rate filtration. Yeah. This one maybe. What you need is basically. One key thing you need here is to actually know the Riemann-Hilbert correspondence with local system conversion. You need to know that the Collier expensive is nice point. To get these Lie algebras, and again, these ones are some kind of organizations. The type variety, organization coming from the theory of organization of greater person. And we're going to look just at what happens for this quotient. Of course, the Lie algebra is the Levy. And here we have theta mu, which corresponds just to the map of Gm to M, that again, because this one is defined in the centralized, definition is dance inside the centralized.
So you need negative. You need negative.
Sorry,
In this,
mu comes from the Hodgkin character.
but I thought.
Yeah, that's also this Hodgkin character that fixes the one role. And I'm saying that the Hodgkin character actually, basically the definition of the name is maps in the center of this grid. So I can take the pullback of this, that's going to be a over guy. And here. Sure. But again, it's going to be enough to use this. Here. Is that geometric synchronization of the full set value. from the idea about G4, so over to this standard squeeze of this squeeze of the extension can actually be computed and essentially follow from this computation and that computation. And the pullback of dual of G naught mapping subjectively onto the dual of this user. This one can be computed in terms of representation field factor. So the consequence finish. Right? Right back. Homology. Okay. The object wanted. But filter the analytic homology of any of these eyes by a level is a push forward of this sheet of a CLA. But so now this guy are eyes of this one the same as the push forward of the homologies of the Sen operator, but the geometric Sen operator. But again, imagine the geometric Sen operator is going to correspond to precisely this part. This one is going to be very multiple. So you can compute this by basically just taking homology of this open linear representation here. Again, this one is just a two multiple G naught, and even the sections. Basically, just I don't know, conquer the complete, conquer lemma, whatever you want to do this. This is the same as we take in the variance. In that there are not like higher than 35. So this implies that these vanishes are equal to 0. And this equality just becomes the homology downside. The of the push forward also for the first of all, I just look at the homology of this thing, taking variance direction of the group, which is basically OLA at infinite level, but can just push forward to this side. Or this one is just the homology of moreover, it can tell you that you have a whole action, but not just the algebra, actually going to be consequence of this theorem, but these guys are going to kill that OLA, so you have an action of this quotient, making this some sort of twisted module, and moreover, that this operator here, because of the full Sen operator there, is basically the same as the arithmetic Sen operator. Okay, I'm going to do something.
So can I ask a quick question? So, you were saying this SH infinity LA.
Yes.
So this, so is there something one? So this is this going to fit into your framework of Jeeves on hypervectoid rings?
Yes. So let me take a couple of minutes and what the expectation of Peter about this kind of things. Actually, concretely, call these geometric interior application more right is going to fit in this paper of representation. So for this, when you go to maybe Schulze, was proven as PLs, you have right this by Young, Let's say the following. So the conjecture says that well, we have this more variety at any level, so yes, and it maps to the flag line. Like the, but conjecture is that well, we have this funny function over here, and so Bobby does no uniformization map and just modify. Then the conjecture is about the existence of some object here. All the use stack. And a Cartesian diagram. And essentially, what this stack is going to parameterize is kind of it's a stack of vector spaces, so we call it a vector space. There is just like a billion varieties in the perfect model of E up to isogeny. So somehow the natural isocrystal can come from an abelian variety, but this cannot be dependent on any just the map here, of course, is going to be using Schwarzschild paper mapping this fundamental group of this universal cover of the any module, sort of the indivisible group into a vector map of this group. So essentially what it's telling you this theorem is that well, have maybe a elliptic curve of abelian variety with like a trivialization in all the data modules. You just need to be given the isogeny class of the abelian variety, meaning just this isocrystal, like mod B as well. And you basically just need to be able to lift the Hodge state Hodge state decomposition of the data model. Like with this two, I mean, maybe the Hodge state will be one random. This is kind of what this is. So what is that? There should be avatars of all these gadgets. Session paper. Let me write down that. So in scientific consideration, we are going to have versions of at least three objects. Actually, we go. Yeah, but I mean, the point that it's the same. It's not changing. This I also want this comparison, but let me explain what this actually is not progressing. So you have going to have some one G that then we call it one GFA. And for example, we're going to look at the same stable locus of this one GFA, and of course, all of these are going to be over the optimization of P1 can make it very similar, but it's going to be over this base. Similarly, as maybe the flat variety is going to live over like the diamond of P. This one is going to be over this potential extraction. This one is going to be this one, of these local analytic groups onto the basic locus. So this guy actually encodes the local analytic pictures in this implementation. Well, he bundles the then, well, we're going to have a ninjas with stack. Chance push a stack. And to define the RAM stacks, the RAM stacks, you actually just need to know the values of perfect groups. You don't care about these important things that are going to be the other avatars in this presentation. Then let's take this one. Okay. The question is that we actually will have a map from 1G, this one. Black variety. Okay. So station of black variety is similar as put their basic diamonds. Here, to find a funny version of this one, the localized version. This guy is going to be a KPLA torsor over the quantization. So essentially, we have the same picture as the diagrams, except that these things are going to be less complicated. Particular, this whole thing, push over, should compute the whole approach to the then maybe this is going to be the whole delay. It's going to be like the prismatic part of the delay, and maybe the infinity array that is just this thing with the local analytic vectors will correspond to the Hodge state part of this. Meaning that it's going to be a array also of the Hodge state status. That justifies the fact that usually this Hodge state stack is just this one model of KPLA. Actually, should come with more clarification. Maybe just a small comment on this. So again, this one is basically a perfectoist and actually produces some isotopes of crystal. Right? If you have a PDB group, the universal cover is a crystal. A crystal, what you can think along thickness, particularly you should be able to predict along these new potent thickness. And if you actually can do that, and this object is kind of independent of the important thickness, so it is not released, you should produce some object that basically only depends on the Ramstadt thing. That's basically should produce a D module. Instead of just a vector bounding curves, should produce a D module with curves. And the point that actually does.
Make this a little bit more precise. I mean, this the existence of this expectation would imply something about what you just said earlier about the theory.
I mean, the thing is that you have this diagram that you can look, for example, at the Hodge state locus here. And well, maybe just need to work a bit more. But at least this is going to produce automatically the amount of the diamond version, this version here. This, okay, let's say by some junctions, we'll end up with the amount of the diamond version, which is more variety to the Hodge state version. And what is left is maybe just do a couple of computations, but this is going to prove that actually this presentation that you get naively from this theory, modulo the stack actually is giving for you this, this version. This one modulo this. I imagine that to actually deduce geometric theory, you still need to know something about the Hodge state homology, maybe versus actually the wrong homology. You still need this. I mean, not to complex one. But at least this one is taking this appear naturally at this. Let's be very